And I'm going to have to edit this recording because I turned it off because I was picking my teeth and forgot I had the camera on. And I figured that that shouldn't make its way to YouTube. I mean, it's not that gross, but it's kind of gross. Okay, let me give him a chance to get in here without my intervention. I think I can disable the waiting room. And I'll go ahead and let it do the join and leave sound. Okay, so it's lesson 10. And today what we're going to do is spend some time in SWM attempting to actually not attempting, I've finally figured it out. Our last example where we had the North Korean mountain blowing up and clogging our channel instantly and causing a change in flow rate turned out to be much more difficult to simulate and SWM than I initially anticipated. And so I had to do some tricks, and I'll share those with you because now that I know how, I'm ready. So when North Korea blows up its mountain, I'll know how to model the flood wave that's going to devastate them. Although I suppose the flood wave would be the least of their worries at that point. And more like, these crazy people are blowing up mountains for sport. I don't want to be here. Okay, enough North Korea bashing because I've never been there. I only know the propaganda I can see on our television, and it doesn't look pretty. So Anna, be thankful you're here and not in North Korea going to a job fair. There we are. Welcome, Jawad, and good morning to you. I got it right this time. And give him a chance to get his audio up and running. And Weston is not going to join us this evening. So he's dependent on the video. Did you just wake up?
No, exactly. I received the mail just maybe 1-2 minutes ago. So
I'm teasing you. I mean, you had that look. I envy you having the just woke up look, because all three of us are like, when is this day going to end? Okay, so what I was doing in the prelude while you were connecting is today we're going to play with SWM and redo our case from last time where the North Koreans blew up their mountain and clogged a channel. And we were able to simulate the water surface of that. And anyway, that was a fabricated situation to justify it. And doing that seemingly simple task in SWM, or HEC-RAS for that matter, takes some modeling. I don't want to call it trickery because we're not doing anything wrong or immoral, but we have to think our problem a little bit differently than if we're writing our own scripts. And I will show you how to do that. So first, let me get to all these open things. Okay, it's not research projects. It's not my, it's probably this one. Let's go with it. Oh, and I'm acting as if you can see my screen. I haven't turned it on yet. Okay, so lesson 10, the usual making of sheets reminders. So that's what we're dealing with. And then the example we did last time was this sudden channel closer. And I've copied last time's scripts into a single cell block, mostly so I can rerun it over again. And right here, we'll set up the conditions that are actually in the problem statement from 0, 60, and 360 seconds. And we'll get some intermediates between that. And right here, I am forcing the time step to stay 15, which is shorter than the requirement by the mesh current number. So we'll be introducing a little bit of what's called artificial dispersion or artificial viscosity, but it'll make the printing easier. We're not going to break anything. And then the rest of it is unchanged from our last time, I suppressed plotting the depth and velocity terms in all instances, and so all we're going to get is the water surface location. And again, I'll leave it to the future to figure out how to capture all these output graphics and put them into a single file that we can animate. And so we'll go ahead and run that. I hope it works. Oh, that was reassuring. And so that's what it looked like before. We had the water surface profile and the channel bottom profile were parallel. And then we blew up the mountain and the flow stopped at the downstream end. So the water depth increased. And that increased worked its way back up towards the upstream end, and we'll stop at, it stops at 300, in this case, 330 seconds. And so there's what our water surface looks like after 330 seconds. So now we're going to do the same in SWM. So in starting to do it in SWM, we can model the same case, but we have to pay some attention to boundary conditions, because in the way SWM is built from an end user point of view, we don't really know that we're dealing much with boundary conditions. But what we can do is we can add an additional link on what's going to be our downstream end, and we'll let it start out life as just an ordinary link, and then we'll let some time elapse, and then we will declare to the model that that link ceases to connect anymore and let it continue computing. It's going to be using something in the program called operating rules. And at the upstream end, we're going to do some noodling also. And to make it consistent with our original problem statement, we'll create a storage element with a huge pool area in it, such that you can think of it as being a tank that's so big that it'll take an eternity to drain. An eternity in our case being more than a day. And we'll mimic the situation, and that's pretty easy to prepare. So rather than you watch me draw stuff, I've gone ahead and prepared a SWM model to save the tedious data entry. So I'll go through the parts of that, and then we will explore the simulation of this case and what we learned in SWM. So in my instance, hopefully it is still up and running. I'm trying to find it, so bear with me. Okay, we're going to need that, because that tells us how to do the magic channel closing. Open, close. We're going to need that. Anaconda. Oh, I may have. Hopefully that is. Okay, let's see if this is still open. Oh, cool. It's still taking input. All right. So here's our SWM model. I'm going to use the drawing tool to indicate our home-brew model. Is essentially that region of this SWM model domain. Remember, in our homemade model, we were able to use characteristic terms on the left side to stipulate that the water surface elevation at that point is essentially fixed. I've added an additional conduit, and then here's our reservoir here. And if this doesn't work, I'll just shift everything left one. On the downstream end, we had a characteristic curve calculation that allowed us to change the boundary condition when the simulation started from a flow rate of whatever 110 cubic meters per second was divided by the geometry, from that value down to 0 in one of our computational time steps. To accomplish the same thing in SWM, what we want to do is instruct the program to run for a little bit. We don't necessarily have to have time 0 exactly coordinated between our homegrown and our SWM model. We can fix that later if it becomes a concern. We want it to run for a little bit and kind of establish whatever its steady conditions are. And then at some moment in time, we want that conduit to cease to connect to the outfall. You notice that conduit has a special name, and I just named it up here in the SWM input stuff. See if it will let me resize that. Okay, that's what I wanted. So I actually just typed in the word last-link for that last conduit. The other conduits have whatever the program assigned count is to them, because they're not particularly special. And then we get here to the left, and then this junction is called storage. It's called Reservoir, for lack of a better naming convention. So the special features, if we're doing the same problem in SWM, are the upstream most storage element and the downstream most last link, and then the outfall. And so at the outfall, I've elected to use a fixed stage boundary condition set at a value of 3.069 meters above an invert elevation of 0. So that is essentially, that's identical to this situation, except the elevations are different in the SWM model because I didn't start at 29. I started at 0. So that fixed downstream boundary condition, if you want to visualize it in our homegrown model, is established at 100 meters to the right of this drawing right here. So you can think of, there's one more connector here that we don't see. The upstream boundary condition, we'll go ahead and explore that in the SWM model in a second. We're trying to maintain a constant water elevation at the upstream end to be consistent with, excuse me for a second. One of the things I hate about Zoom, and actually Microsoft Teams has its same quirks, is that it puts useful stuff in the way all the time, what they think is useful. So I'm returning to our SWM model, and let's examine the upstream storage reservoir, and then we'll look at the, well, actually, let's do the conduits next. Let's pick conduit 5, and let's go take a look at its setup. It's set up with a bottom width of 20. The left and right side slope are set at 2:1, horizontal to vertical ratio, and that is pretty much consistent with the problem statement. 2:1 horizontal to vertical, 20 meters bottom width, and a very 10, 100. Oh, I actually got my slope wrong by a factor of 10 in the SWM model. I'm surprised it worked. That's kind of cool. We'll go ahead and fix that in a second. So I have each of these at a length of 100 meters, and let me check the elevations now. If they're 100 meters apart and our bottom slope is 1, 2, 3, 100 meters, moves this 1, so it goes 0.001, and I'll make sure that is the actual input. Okay, I did have a different longitudinal slope in our computer simulation. So my SWM model and this model agree. If that extra 0 was there, we can go ahead and explore that in a minute, see how that works. So these all have the same geometry, and let's just pick an arbitrary interior junction They have a invert elevation, and the invert elevations differ by 0.1, a tenth of a meter, 10 centimeters as we're moving upstream. And if we were to construct a profile, should look as expected. Ignore the fact that there's water in it already. I'll explain why that's there. So here's our plan view of it. And these are supposed to be sloping down. Let's see if it will redraw it with any degree of slope. The last special link here is the connection from the reservoir into our channel. All right, the reason the water looks this roughly at the same level is we put a starting depth in every connection, every junction at 3.069. And I will just verify that they're all starting there. And this should be 3.069 above zero, it is. And that one should be 4.069 above zero because we have gained 1 meter of elevation over a kilometer of run. All right, let's go examine the storage unit a little bit more. So a storage unit, you can think of it as just a big old bucket, and we have a choice of how we want to represent storage. I've chosen tabular, which is called a storage curve. There's another option called functional curve. A functional curve is not a good choice for this particular example. And in the practice that I've done using SWMM as a integrated hydrology and hydraulic model, I only use the functional curve when I am actually initially building a model, because it helps you make sure everything has adequate connectivity. And then you go back and you'll use a tabular storage curve. So I've named my curve Big Reservoir, again, because I have absolutely no creativity when it comes to naming things. And if we look at Big Reservoir, everything is measured from the bottom of Big Reservoir. And if there is 0 meters of depth in the Big Reservoir, there is no pool area whatsoever at all, nada, oopso, nothing. We get a tenth of a meter of depth over our reservoir, and I've stipulated there's 5,000 square meters of area. Gets 1 meter deep, 50,000, 2 meters deep, 500 million, 3 meters deep, 600 million, 4 meters deep, 700 million, 5 meters deep, 800 million, and 5 billion square meters if we get all the way to 10 meters deep. And so what that does is keep in mind that we're starting somewhere between 3 and 4 meters of depth. So we roughly have 700 million meters of area times 4 meters of depth. So what's that? 2.8 billion cubic meters of water available to run down this itty bitty channel that's 20 meters wide and 3 meters deep. So if it's going to drain and go empty, it's going to take a while for that to happen. And so what we're doing is deceiving the computer program into treating that as essentially an infinite reservoir. And if it turns out that our area choices are poor for that, it's a small matter to go back and make them bigger by simply adding zeros to these. Our computer program gives us a way to visualize what we've done. Before I bring up the view, I want to warn you that it's a analyst assistant. It's not intended to actually really represent any sort of storage curve. So what we can see from looking in that curve is the vertical axis in this drawing represents depth above the bottom of our storage unit, and the horizontal width, and it's intentionally centered. The wider it gets, the more surface area that reservoir has. So down here at very low depths, our reservoir doesn't have very much surface area, and we've created a situation where once it gets a little bit more than 1 meter deep, oh, it won't let me do what I want to do, so there's no point in trying. Once we get more than 1 meter deep, we start getting a whole lot of area. And when we go from 5 to 10 meters, I've just made it absurdly large. So keep in mind, our model is starting with that much volume in it. And the reason I provided more depth than the initial conditions is because as that water wave propagates back upstream, it has to have a place to go. We have to be able to put volume into that reservoir. We won't see any change in depth that is meaningful for us, but computationally, it allows the water to have some space to go. So I'll press the okie dokie button. And let's go over here to a thing called control. And I've gone ahead and created a control rule. And I'll go ahead and bring up the rule. And the control rule goes by the very cryptic name of rule number 1. And in what I've done is in rule number 1, I've stipulated that if the simulation time in decimal hours gets bigger than 1 hour, then the conduit named last link is going to have its status set as closed. Otherwise, so when that condition is not true, the conduit named last link will have its status set as open. And what we've been using when we've done these few swim simulations up to this point in time, the default, if we don't specify otherwise, is conduit links start out life as open. So again, think of what's going to happen. Our simulation is going to run. It's going to do its simulating thing. It's going to be delta t-ing, updating, delta t-ing, updating. And then once the elapsed simulation time is greater than 1.0 hours, we're going to close off that last link. We're going to go ahead and flip the switch on the mountain explosion button, and boom, we'll fill up our channel, and that link can no longer carry flow. So how did I figure out how to do that? Well, first thing, I went to an online resource called OpenSwim, and I actually typed a search of how to close a conduit in swim. And this is what came up. Somebody named Kirby McRae, and I think if I was to look, we could figure out when this was set. It says, here's what I do in EPANet. How come I can't do it in swim? And then Robert Dickinson, who happens to be one of the programmers of the computation engine in SWM, gave this answer, which at first glance doesn't look very useful, but if you've never met Bob, that's actually a pretty tempered answer from him. He's an impatient human being. Probably because he spends much of his waking life talking to a computer. And then another person named Rob James, he's a Canadian from Canada, suggested that you could do something like this. Okay, so that was a good help for me trying to reverse engineer this particular problem. None of this tells you exactly how you can get those control rules put into SWM. So I made the next horrible engineer modeler mistakes is I opened up the user manual. And let's look at what page it is in the user manual, page 222. But if we go back up to where it started, so I typed in the word control rules. And it says a user rating curve, control rules can be used to dynamically adjust flow when certain conditions exist. The principal input parameters are, and that doesn't tell you how to enter a control rule, but it's a start. Go to item 2, and it tells you what a control is, but it doesn't tell you where to enter it. When you get to objects, there's the control rule, still nothing. Control rules, still no use. And then finally, okay, control rules editor. And that was a useful piece of information because if there's a rules editor, then we return to our computer program and we start looking for things that look like editors. The ones we're used to are links. And down here, we have all these options are blanked out right now. There's nothing we can do with a high-level link, but I can pick a conduit, I can add a conduit, I can edit an object, and that was the key. So in our case, we go to controls. We can't add a control. I think I could probably delete it, but I don't want to, but we can edit the object. In this case, that's my control rule 1. I'm not sure how to add a new control rule, but it's trivial to just keep editing in this sheet. And we could create control rule 2. And because I'm in a frisky mood, we'll go ahead and we will do a control rule 2. Oh, but it won't let me have a paste option, will it? Copy. Paste. So let's go ahead and set the case. When it's bigger than 1, we close things and we'll give it a different kind of condition. We'll just close it briefly and then we'll open it again, which is different than our problem, but mostly to figure, okay, so and, we use the and keyword, AND SIMULATION space TIME, bigger than 1, less than or equal to. How long do you want to leave these rocks in the downstream end? Again, we're in North Korea, and if we believe global propaganda, we offer all the people that are left after the mountain blows up a huge buffet if they pick up and move rocks. And so about 4 hours later, those rocks are gone. And so see, that's less than or equal to, so that can be a strictly greater than. So we're actually programming the SWM program itself. It's a weird concept. When that becomes true, link status is open. And I don't think we need an else condition. Okay, if it's bigger than 1, less than 4, we close it. Otherwise, it's open. Oh, we don't actually need this second rule, but we'll do it anyway. And if it gets bigger than 4, we'll open it. I just wanted to show the syntax of how we create a rule. And we'll find out in a second if it's going to behave for us. So now we can run it. Oh, and it didn't get angry at me. That's very rare. Let's go back to our other control part. And let's play with our general things. So we're using dynamic wave flow routing. We have no infiltration to matter, but it has to have an infiltration matter. So this is using Horton, who heard a who. And we have starting dates, and currently we're simulating 6 hours. Our own example, we went 300 seconds, which is 5 minutes. So let's get our time steps down to something, at least get it to report. We may regret that choice. Choose OK. Oh, I forgot one thing. Let's be sure we have the inertia terms on. So this is as close to our model as we can get. In our case, normal flow, we would base it on Froude number. All right, hopefully I didn't break anything. So we run our simulation, looks good, and here is our initial output at 1 minute. And these are supposed to be parallel. I must have some subtle input error here, but I will accept it for the purposes of this discussion. So you can see there's a little bit of wave action, which is a consequence of the numerical method, and all of a sudden that downstream rocks have been filled in the channel. And we watch the wave move back and forth. And so the question I have, this is at 1,100 meters in, and I was turning that conduit off, junction 11, junction 10. Oh, okay, I got it. So position 12 is my outfall. Position 11 is where the rockfall occurs, and so that is now behaving as expected. Pretty much parallel, then the rockfall occurs, and now we can see the water is bouncing back and forth. Look at the left edge. You can see at the left edge, our reservoir is more or less holding constant. And after 6 hours, we have that. Let's go ahead and grab our flow depths at nodes. Let me see if I can get the head would be depth plus elevation. And so we want to catch, in our case, our node 11 and our node 10, and then we can go take a look at our homebrew result. So we'll take node 11. Oh, graphical user interfaces. How I dislike these sometimes. Node 11, node number 10, node number 9, go node number 8. I think we can go up to 6. That should be plenty. We'll just do those 4. So in our case, our node 11 is our most downstream node. Node 10 is interior to it, and then node 8 is a couple of nodes different. So we're supposed to start at 3.06 deep, and we're close. There is instability that's a consequence of a dynamic wave routing method. But as soon as the rockfall hits, it goes from 3 all the way up to 5. Now, in comparison to our homebrew model, time 0 in our homebrew model is right between those two cells. So 4.87 represents 60 seconds into the simulation. Let's see if our water in our homemade model appears to be at elevation 4 units at 60 seconds. Naturally, I didn't prepare it quite like that, but what is our most downstream node? Happens to be, let's see, y of n. So we're just going to go ahead and print downstream depth. And we'll rerun it, and it should appear, there should be just right after each of the plots, we should be able to get the downstream depth. So did the first one, made the plot, it did not print it. So what did I do stupid? Print DDN. Oh, maybe we should put it every place where we want to print stuff out. That would be less of an act of dumbness than one would expect. And now my mouse has decided it's going to do stuff that it wants to do. All right, let's try that again. So, okay, so at time 0, our depth at the downstream end is 3.069. At time 60 seconds, it's 4.09. Let's see what we got in SWM. At 60 seconds, we have 4.87 in our SWM model. And that's actually more close than I would have expected it. Let's modify our SWM model to run at about a 15-second time step, because that's what our homebrew model is, and see if that changes things very much. So we'll go to our options. Okay, routing step in seconds. Set it at 15. Let's see if I can figure out how to turn off any adaptive time stepping so I can force it to stay to 15. Turn off the variable time steps. I think that'll work. Okay, that may not have been such a bright idea. I don't know what I just broke. Wow. Incredible. Okay, routing is fine. Go ahead and dampen inertia real quick and see if that improves anything. Take a look at the that seems to behave the way I expect it to. Except with the inertia damped, I don't think we are solving the same problem anymore. So let me turn. We'll keep the inertia terms. Choose OK. Let it run. Did that actually take my input? That was, It's bizarre. It looks like we have to use adaptive time stepping. All right. So let's return to in our SWMM model, our depth at node 11 is 4.87. In our home-brew, our depth is 4.09. Let's actually print the next one. Getting to the point where I'm forgetting how to count. And it's not too hard at this point to realize that in a practical sense, we probably want to use SWMM. Okay, starts out that we have 3.069069, 3.094, and 3.96. Now, unlike our homebrew, SWMM is not using a lax diffusion scheme. It's using a different type of solver that has much less artificial viscosity. So it's arguably doing a better job at capturing the influence of that downstream changing. But what is important is that the behavior is consistent with our homemade ones. We were doing it at, let's see, 60. What's the other one we want to check it at? It'll get better as we get later in time. 0, 60, and 360 seconds. So let's see what we got at 360 in our homebrew. Oh, it would have been nice if we actually went to 360. In our case, in our homebrew case, our flow depths are roughly around 5.14 meters after 360 seconds, which would be 5 minutes. So we would go at let me get the transition occurs. Okay, that's minute 1, 60 seconds, 2, 3, 4, 5. So now we're at 528 and 533, which is somewhat deeper than our home brew, but what's important is the space between the two seems about right. The downstream one and the one next into it are about the same value. And if we played with our homemade one more, we could get it to agree more and more with SWMM. But my point here this evening was to illustrate how we would construct a case in SWMM when there's a sudden flow change. And we set our things that after 4 hours, it should start to try to go back to normal flow. And let's just watch that in the animation because it's cooler. So we're hour 1, 2, 3. At hour 4 is where our rocks are removed from the channel. So it's coming up on the guitar. Wait for it. There we are, 1 minute after the 4th hour, and now that conduit again is available to conduct flow, and so it starts moving downstream. And if we ran it long enough, we would see that we would revert back to our same initial condition. All right, let's go make some refinements since we have the SWM model here. Let's see what we can do with the storage reservoir. To try to end this discrepancy of this in. So I think the depth in the storage reservoir actually has to come down a bit. So let's take a tenth off of that. So 3.969. And sadly, this is the kind of shenanigans you have to play with a professional quality code for making a simulation. Huh. That was okay. I bet the next one in is my mistake. Okay, so I have intention. Yeah, we're a consequence of its downstream boundary conditions. So there was nothing we did wrong. Let's go ahead and put back to the correct value. And let's look at some other things while we have this up and running before we move on to our next example. We could, instead of having a fixed outfall, state that we want normal flow on the last part. Rerun the simulation. And now let's take a look at what happens when we establish a normal depth. Really not much different than before, although we may get to nearly, no, we won't get to nearly parallel. 54321 So that's the closest to the equilibrium condition that we started with our homebrew simulation. And it's actually looking more and more like the homebrew. Huh, cool. I'm going to disappear the profile and we'll redraw it, and we're going to play some additional shenanigans. Remember I said that it was just these interior nodes? We don't have to use the obvious starting and ending node. We can instead explicitly create a profile. So I'm just going to go on what would be the interior nodes, and we'll take a look at that. And then we'll be done with this particular example, and we'll move on to getting set up for the next one. Okay, so that more or less 100, 200, 300, 400, 500, 600, 700, 800, 900, 1000. Okay, so that is conceptually identical to our homemade simulation. And 0 starts at 1 minute, so let's get close to 0. Okay, so here would be what our homemade simulation would be like. 1 minute into it, we see that we have we'll go with depth, 11 and 10. So those are the two things that we have outputting in our model. Huh, that's weird. These numbers don't make sense to me. At time 0, the depth at node 11 should be 3.06. So did I make a mistake? 3.069. That seems right. Well, that's bizarre because obviously our homebrew is way better than anything that a government agency could possibly produce. There's some difference between the two, but the general pattern we're picking up is the same. We see our wave propagating upstream and then starting to work downstream, upstream, and 16 minutes into blowing up the mountain. So these waves bouncing back and forth, they'll do that for a long time in a channel, except we just took the rocks out. All right, let me save that. And actually, I'm going to call this as EXAMPLE3. And I'll have to figure out a way to download that so I can put it onto the class server. So if you want to explore this on your own, you don't necessarily have to build it from scratch. This is not a hard simulation to build from scratch, but it has certain aspects of tedium involved with it. I'm also going to save it as example 4 because actually no, I won't. I'll cancel that. I will go ahead and create a new project and leave it there, and let's go look at our next example. So we've explored these two cases in SWM, and while they're not identical, the overall behavior is similar, and so we have self-learned a component of the way the boundary conditions are handled in SWM. More importantly, we've learned how to do sudden changes in things in SWM using control rules, which is generally an advanced topic. Let's go to our next example. We won't complete this one today because I haven't got it completed yet. But let me re-render that. There, I wanted. So this is taken from my favorite book in the history of the world, Elements of Computational Hydraulics by C.G. Kuditas. This is example 4.1 on page 70 of that particular textbook. And we have a copy of this located on our class server. That's the one that I always have to download and rotate. And it's in numerical order, but the pages don't look right. So you have to take some care to find your way to that one. And this is a pretty interesting problem, one that is ostensibly unreplicatable in reality, because the initial condition is not necessarily realistic. What we have on the right side edge is a free overfall. So if there's flow, we know from our hydraulics classes that it's likely to pass through critical depth depending on what the flow rate is. And the critical depth is a consequence of the channel geometry. In this case, it's a 29-kilometer long trapezoidal channel with side slopes of 1, so it's a rectangular channel. New spelling for angular. And we're examining a channel that has a apparent bottom width of 1 meter. So a 29-kilometer long, 1 meter wide rectangular channel is again kind of a silly thing, but we can think of that as certainly a starting case for something realistic. We're going to initially attempt a longitudinal slope of 0. So this is just a flat table, which also is unrealistic on the Earth. Anything 29 kilometers long is going to have different elevations at each end. Except maybe stuff that they make at particle accelerators and stuff and things like that, where they actually put a lot of effort into keeping stuff perfectly flat. But I don't even think the big ring accelerator in Switzerland has a path distance of 29 kilometers. I could be wrong about that. I mean, it's big, but not that big. And at this left end, we have an input hydrograph called Q sub 0. And here's a diagram of the hydrograph. And so at time 0, there's 0 input, and then it rises quite rapidly over a course of, let's see, 1 times 10 to the 3, 1,000 seconds. So 600 seconds is 10 minutes. Basically, over about a 15-minute period, it goes from 0 to 100 meters cubed per second per meter of width. Now, 100 cubic meters per second of flow in a channel that is rectangular and 1 meter wide, we expect the water surface it's going to have to raise up a considerable distance. And then after that 15-minute period, it has a linear decline back down to 0. So this is our hydrograph boundary condition. Now, if we were going to make our own homebrew one, first thing we need to do is to deal with the hydrograph. And here's our hydrograph right there. And the only problem is the way the computer program read it, it missed this 0 here. So we'll just go ahead and manually fix that. So at 0, we had, let me go ahead and fix that, 1.1. Okay, so that should give us a proper hydrograph. And let me explain how I will split the cell, and I'm using another package that I had to find off the internet. We don't need to use this package, but I was in a hurry, and so when you're in a hurry, it's easier to use other people's work. So we read the hydrograph, and for some reason, it took that initial condition, the 0 flow rate and the 1.1 cubic meters per second, and turned those into column names. And so it said column 0 is time, 1.1 is discharge. And that's one thing out of 640 lines that's wrong. So it's easier in this instance to just override it. If we were going to use our homegrown thing over and over again a lot on different hydrographs, we would actually formally repair it, where this step would be somewhat automated instead of a manual override. And so I'll go ahead and I'll add that initial pair of data, and then I'm going to take from column label 0 everything and declare that equal to time. Column label 1, declare that equal to input flow. And just for fun, we'll plot it. And so there's our input hydrograph, and we have to ask ourselves, does that look right? And I immediately think it doesn't look right. So let's see what's going on. Okay, so in the first 1,500 seconds, first 3,600 seconds, it goes up to 100. So let's see if that's indeed correct. Maybe that's at 3,600. I can't tell by looking because we plotted all this other stuff. So there's our input hydrograph. Essentially a nearly triangular spike coming in to our channel. let's go ahead and play with that using the SWMM program, because that will be easiest, and then we will go back and figure out how to do it with a home-brew. Let me see if that actually is going to work. Okay, so that should be copy. Hopefully the APIs work with what I'm attempting to do. So what I've done is, I think I've copied those two columns, and now I want to try to load them into my SWMM program. So I go back to SWMM, and I'm going to need a oh, I actually have to create stuff first, don't I? What a piece of junk. All right, fine, we'll do it your way, Mr. SWMM. We're going to need an upstream node, so there's 29, 28. There's 29 kilometers, 28, 27, 26, 25, 24, 23, 22, 21, 20, 19, 18, 15, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, kilometer 1, and then kilometer 0 in this case. Since it's a free overfall, we actually can just put it right in there. So we've now created our free overfall. We'll leave everything at elevation 0 because the actual problem statement is elevation 0. Each conduit is going to be a rectangle. So we'll take care of that. Its bottom width is 1 meter. And we're going to need to, let's let it get really deep for the purposes of computation. And the .025 is our Manning's end. Flow units is going to be then meters per second. We're going to use dynamical wave. We don't care about force and aim because we won't have, and each conduit is 1,000 meters. Press the OK. Now we have to build our drainage system. So in practical integrated hydrology, hydraulic modeling, you tend to do things a little bit more interesting than straight channels like we have here. But we're going to start with the straight and narrow and then work our way to branches and then work our way to a quasi two-dimensional representation. And by the end of that, we will be ready to do water quality computations and basically be very dangerous engineering analysts by the end of the class. Able to turn clients' monies into catastrophic mistakes in a matter of minutes and blame it on somebody else. Otherwise, we wouldn't be much of an engineer if we couldn't do that. So that, I think, has the setup. And now I need to, oh, I'm going to do a sneaky way to run a hydrograph. See if I remember how to do that. I'm trying to avoid doing a rain gauge and a subcatchment, but if I have to, I will. So I should be able to provide a time series. Inflows. Ah, there's what I want. I want to be able to edit a time series on the inflow. So this is going to be the input hydro. And with any luck, we'll be able to fake this without having to actually read the instruction manual, because we wouldn't be a very good engineer if we read the instructions. That's just not how we act. I'm kidding. Okay, so highlight both those. Choose copy. Switch to the remote desktop protocol. It's giving me paste as an option. Let's, oh, you piece of crap. Plan B. I'll be a little sneaky here. Since that is on our internet, let's go to our friend Firefox and get our little spinning thing. So I'm even though I'm doing with network lag, I'm still really happy because I'm on a Macintosh computer and I'm able to deal with this Windows stuff without having to deal with it. So let's start a new session. Okay, so 54. Good, I remembered the URL. And we are in this class. We are in what I think is lesson 10. Presentation. See if I can open the file. All right, that's perfect. So edit, select all, edit, copy, go to SWM, edit, paste. Oh, you piece of junk. It didn't do it as 2 columns, and that's because it doesn't know what to do with that comma. So let's try some super duper tricks. I'm going to, this may be the best thing to come out today. So we're going to go ahead and find comma. Really wonder why it is down there at line 2000. Let's go up here. Edit, find comma. Cool. And I want to do a find and replace. Should be replace comma with 1, 2, 3, 4. Let's see if that parses correctly. We'll select all of that, copy it, go swimming. Gotta love it. Got to love it. So 4 spaces didn't parse correctly, and I don't have on my Windows install a spreadsheet type environment. So let's see what we can do to, do I want to save the changes? 9. We're close. We'll get there. We need to prepare that file a little bit better. So we need a file that is just a value of time, and we need a file that is just the value of the hydrograph. So let's see if we can write the contents of a file. And I'm looking at my other notes to see if I. Oh, seriously, there it is. Nothing computational wants to work today. So we'll make a guess. Pandas, right? And we give it the name of what we want. No, that's not the right syntax. We'll do this actually the really hard way, but this should get us then. We're going to print the value of time. Then we're going to print blank line. And we will print the value of Q input. And we will cut and paste those to an external file by hand. I hate computers sometimes, and now happens to be one of them. Edit, split. Still isn't going to do it for me, is it? Print time, don't take shortcuts. All right, we're going to have to read how to write to a file. And as usual, we'll get mostly useless help. Okay. Write a CSV file. So we put the name of the object, we use the term to CSV, and there's how we get the file. I guess that isn't that hard. Okay, so name of the object, TIME, to underscore CSV. Hope that works, or we're going to get the, yeah, of course it doesn't actually work when you do it in real life. Data frame to CSV.
There will be colon.
Pardon me? Oh, maybe because I didn't give it a name. All right, they both exist there, so we should be able to get to them from our kind of want to know what I did with a swim. There it is. I'm going to minimize this so I can try to mess with my Still didn't achieve what I wanted to do. It also didn't write the whole file. Maybe there's supposed to be 640 elements in it. That's well, I'll do this offline and get it all prepped and built, and we'll pick up from here next. So what we're trying to do is enter the second column of that in the time domain for inflow in our time series thing. So we want the time, and oh, actually we have more work to do anyway, because SWMM wants it to be in hours and decimal hours, or we actually have to use a calendar date and time input structure. So we will, I'll figure out how to do that and bring it back next time. Plus, give me a chance to prepare our homebrew version. After we do the homebrew of this problem, we're done with rolling our own cigarettes, so to speak, and we'll stick entirely with SWM. The first part, the reason I spent this time on it is that I want you all to leave with an appreciation that what goes on inside SWM or any other professional code is fundamentally quite straightforward. They do a better job than we can do on our own because they've had 40 years to work on it. But fundamentally, all it's doing is some kind of finite difference scheme, and if necessary, we can replicate it on our own. More importantly, doing our own was what informed us on how to start monkeying with boundary conditions to simulate the rock fall falling into the channel. And we will use that same kind of intellectual questioning to look at other boundary conditions for some more realistic and practically valuable simulation cases. So that's what I have for this evening. I would have expected data to cut and paste better than that, but sometimes that just happens. And it's not a complete surprise because the authors of SWM had no idea where the data is coming from, so there was no reason to expect the application programming interfaces to be entirely compatible. Worst case, what we'll have to do on the Amazon Light Sail instance is create a, since we have an Anaconda script there, we might actually just have to take the file and create a little script there that parses the file correctly so it can be dropped into SWM. And I'll have that by Monday. You can do it on your own if you want. It probably would take any of you less than 2 hours to do it the first time. And then if you're smart, which I'm apparently not, you would save that script somewhere so that you could go use it in the future. So I'm going to click, I say OK a lot. Now I know why. It's because it's this button right here. I'm going to click OK. I'm going to exit the dialog box and we will continue with this example later. So I guess now I do need to save that. I'll save this as example 4. And let me leave a note in progress. All right, cool. I'll put those input files. It just dawned on me. I'll put those onto the server so that if you all don't want to do them yourself, you can just download the file. The way you open a file in SWM is you choose in the file menu, you pick the word that looks like open. And by default, it's looking for a file that has the extension .inp, and you just open it, and there's your file. And so those INP files, they are easily, they can be emailed. So if I were to email it to you or you download it, it should almost construct this same picture. The drawing might be a little buggered up, but the rest of it is unchanged. And I'm going to go look at the contents of one of the INP files right now. I want to look at file 4. I want to see if the file 3, I want to see if the control rules actually are stored with the file. It looks like they probably are. Open with, give me some choices, please. We know you have a choice, but we're not going to give it to you. I'm going to open it with, oh, don't want to use WordPad, I want to use Notepad. Okay, so if you end up using this program a lot, this file will start to make sense to you. In some cases, when I'm doing swim models of real things, sometimes I just edit the input file directly because it's easier. So this was example number 3, which had big reservoir. And let's see if oh, good, it does store the control rules with the input file. So all you need is an input file to get a swim model to run. There are some cases where if you have external files, it will store the path and file name to the external file. If you don't provide that to your end user, that external file, they can't run the model. And the name of our our case where the storage thing goes is nknuke. I guess I was just having fun with that. All right, well that's all for tonight. I want to thank you for your attention. I will get the video posted probably by tomorrow, and we will continue on with our slow but steady foray into integrated hydraulic and hydrology modeling. So far, we've stuck with hydraulics. Today, we brought in a hydrograph, so we're starting to work our way into hydrology. With that, I will call it an evening, and I want to thank you all for paying attention and trying not to fall asleep. Have a good evening, everybody. Have a good day, Juan, and hope the rest of your day goes great. And the rest of you all, see you Monday. Have a great weekend and take care.
Good weekend, you too.
Good weekend.
Bye-bye.
Bye-bye.